Alrighty, guys, good morning and welcome back again to Algebra 2 today, or no, Algebra 1 rather. And as we get rolling, obviously I am out of the room today. I'm out for a PD training for our Algebra 1 curriculum. So I'll be back when we come back on Monday of next week for our next B day. In the meantime, I have for you guys a recorded version of the lesson for 3.2 that you're going to work through here with the sub. A lot of this is going to be kind of directed by me just to make sure that we're capturing some of the larger concepts and the larger ideas that we want to introduce for the lesson. But it's going to be building off of what you guys saw from the first lesson with 3.1. And you'll have some time to kind of compare and contrast and work through some of the analysis for yourself. This lesson is titled Floating Down the River. And we're going to continue kind of working with this intuition of doing analysis on functions, identifying like the key characteristics of behaviors. For those of you guys in my class, we have our cell phone slot assignments, always shown here in our slide deck. So as you're coming into class and you're filtering in and getting into our Schoology account to find the video lesson, please definitely make sure to bring your phone up to the correct slot in the wooden caddy. The sub knows that you have assigned slots for the phone, so they should be there during the time in class. Otherwise, I want to get launched right into a warm-up for our work for today. In particular, I have for you guys some of the retrieval problems on pages 17 and 18 that I want to take another quick look at just based off of where we're at with our day one material. I think a lot of people are maybe struggling with these. We've got two functions. One of these guys is named f of x and the other one is named g of x. Our goal here is to try and sketch a graph for these given functions, shown to the right over here on this grid line. So what I want you to do real quick is maybe take a first attempt at sketching the graph for both f of x and then g of x on the same set of axes. Try and think about, like, for a linear function, what's the y-intercept and the slope term with this particular format. I'll give you maybe a minute or so to kind of mull it over here, but then I want you to unpause the video and kind of take a look at what we're working with, and we'll move from there. All right. So with these functions, f of x or g of x, I think some people maybe got thrown off on the first go around with the fact that we see g of x is like the name of a function, where usually we're seeing something like f of x. It's just a different name. It's still behaving the same way as f of x in the sense that it's a linear function. It's just a different and distinct one. We don't want to confuse them, so we give them different names. When I'm trying to graph a linear function, what I want to start to identify is what my y-intercept term is and what my slope term is. If I'm thinking about my y-intercept, one thing that always helps me figure out what exactly that's going to be in this sort of function definition template is to think about what happens when I'm looking at a graph. A y-intercept is always going to happen when a point is on the y-axis of the grid, right? That also means that the x-coordinate anywhere for that point along the y-axis should be 0. So if I want to find the y-intercept for a given function, I can try plugging in x equals 0, and I can see what I'm going to get out of the algebraic expression. So for f of x here, if I were to plug in x equals 0, and I wanted to simplify down the result to find the output, I'm going to do -5 times 0, which is 0, and I'm going to take that result and I'm going to add 4 to it. So in this case, I get a coordinate at 0, 4. From there, if I wanted to think about what's going to happen next, that's where this other number, this -5, is going to come into play. What I'm going to say here is that my slope is just -5, or if you prefer to see it as like rise over run, you can divide that by 1, and it won't really change the value, so it's still equivalent. So you can think of this as saying like down 5 and over 1, down 5 and over 1, down 5 and over 1 to the right. So you'll get kind of a linear function that's decreasing in this given context. If you wanted to run it backwards, you can go up 5 and then left 1. So that would be kind of like a full version of the graph of f of x shown there in red. We're going to do the same thing here for g of x, where if I want, say, that y-intercept term, I'm going to plug in x equals 0. I'm going to figure out what I get as an output. Anytime I'm looking for a y-intercept, this trick always works because the y-intercept is by definition on the y-axis where the x-coordinate is always 0. So I'll do 2 times 0, that's 0, and then 0 minus 3, that's going to give me -3. So I'm going to start my graph down here, and then that means this 2, that's the slope term. And if I wanted to write that as a fraction for rise over run, you can always do something over 1 without hurting anything. It's going to ultimately give something equivalent. So as I go, I can take my y-intercept coordinate as the beginning place for the graph, and then I go up 2 and right 1 to get kind of the first part of the graph. If I wanted to reverse it, I'll go down 2 and left 1 so that I have the same kind of straight line behavior for this function all the way through its domain. Now, what you'll notice is that these points are ultimately intersecting at a given coordinate. In this case, this coordinate is like 1 comma negative 1. And probably should have chose a different color there. That's kind of hard to see. I'll write it maybe in green. There we go. It's at 1 comma negative 1 that those points of both of those lines are exactly on top of each other. Every once in a while, when you're graphing functions, you'll see that they intersect like that. And it's actually a useful characteristic in the sense if you wanted to go on, say, in like later in Algebra 1 or in Algebra 2 to solve a system of equations, or to solve, say, when one function equals another, you can use a graph to help to figure that out. That's kind of neither here nor there for what we're going into for our time today. Just a little extra practice. On page 18, we're focusing on writing some rules for relations that are shown in the table here. What I want you to think about real quick with your group mates is how's the pattern changing? Would you say this is like a linear versus an exponential pattern of change? And then once you have that, maybe focus on like the explicit rule. A recursive rule is sometimes helpful to kind of help us work through the process of where we're starting and how things are changing. But I really want to emphasize that idea of the recursive approach instead of say, rather the explicit approach. All right. So for these patterns of change, one thing that I'm noticing is that in both of the tables, I'm not necessarily starting at an input of 0. I'm starting at an input of 1 in this case. So from there, if I'm trying to think about the pattern of change, one thing that I might need to think about is kind of a potential offset, but I'm still thinking about the f of n values or the g of n values, the outputs, and whether I'm adding or subtracting or even multiplying or dividing by something to either increase or decrease. Here, what I'm going to notice on the left-hand table is that every time I increase n by 1, it looks like I'm decreasing the output by -3. So going from 64 to 61 to 58 to 55, I've got this consistent -3 pattern. So if I wanted to write an explicit rule for this guy, I have to think about, okay, I got to capture that pattern of change. So I'm doing like -3 times a certain quantity. I'm starting at an output of 64, but notice that that's not at the 0th input, it's at the first input. So if I'm starting at the first instead of the 0th value, I'm going to have to think about like an offset here where I want this n minus 1. And that kind of goes back to what we saw back in Unit 1, but also this idea of point slope form from Unit 2, where sometimes the table's not starting at 0. So we're thinking about what we have to do to go back to get back to that y-intercept. For our other table, what I'm going to notice here is instead of like adding or subtracting, I get kind of a different pattern of behavior. It looks like I'm dividing by 2 every step of the way to go from the previous term to the next term in the sequence. If I'm thinking about division by 2, the other way that I can think about that is multiplication by a half. And that's usually what we talk about when we're working with like an exponential function in this context. So usually I want to avoid that idea of saying I'm doing like division by 2 in an explicit. Here I might say that g of n is starting at an initial value of 64. It's being multiplied by a half to a given power, but I've got to worry about the offset, right? It's not really starting at the y-intercept. It's starting at an input of 1. So to go back to that, I've got to do n minus 1, and then that's going to be my explicit equation for this guy. So it's a little mixed review there from what we've been seeing from some of the stuff in Unit 1 and in Unit 2. As we go forward into Unit 3, though, we're kind of switching gears and focusing a little less on writing explicit equations and talking more about the key characteristics of a graph or a table for a given function. We also introduced the idea of how to write what a function is in terms of, say, like an explicit definition versus just a relation. And we're going to continue to build on some of these ideas as we go into our lesson for our time today. We're going to take our first CFA assessment, probably our only CFA assessment for Unit 3 on October the 29th for you guys in the B-Day crew. If you're still working through some summative retakes in Raptor 101 or Raptor Academy, don't fret. This deadline for October the 10th before fall break, that's mainly for people that are completing it in the testing center. I think Raptor Academy is just a little bit behind. So I want to make sure that they get all the time they need to get you guys where you want to go. Otherwise, Unit 3 is going to be pretty short. We're going to start getting prepared to wrap things up as we switch from October into November. The semester is definitely going to speed up as we get closer to winter break. We got fall break and then Thanksgiving break and then winter break, all kind of packed into the same quarter. So as we go, definitely make sure that you're working through the ready, set, go problems. You're getting submitted as you go. So our goal today is to continue to refine this idea of what the key features of a function are. And we're going to use a couple of different representations to do that. We're going to talk about graphs. We're going to talk about tables. We're mainly going to use those types of representations to kind of pick these things out for a given function. We're also going to have a little bit more of a discussion for how to express collections or sets or spans of values from beginning to end. We're going to kind of introduce this idea of interval notation and really reinforce that as we go forward. We've maybe talked a little bit about this in 3.1. There's a lot of different ways to write collections or sets of values. But as we go forward, we're really going to emphasize interval notation because that's what you're going to see the most of as you move all throughout the high school math curriculum here at Eagle Crest. So we've defined what a function is. A function is a relationship between inputs and outputs. You give it an input, you get an output somehow by following a rule. But sometimes those relations are very specific. A relation is a relation if for any one choice of input, you get a bunch of different outputs. So notice here on the rightmost table that when I choose x equals 0, I got two distinct outputs for it. Could be either 6 or 8. It's ambiguous in that case. That's what we refer to as just a relationship in mathematics. When we say a relation is a function, that's usually a little more specific. So if you look at this leftmost table and any one choice of the values for x, you don't see any repeats. There's no two same values of x's going to two distinctly different values for y. One x maps to at most only one value for y. So when you hear us refer to something as a function in algebra, it's a very specific definition that we're referring to for that very specific kind of input. The other thing that we've introduced is that when you're working with a function, especially with a graph, there's certain key features that we're usually interested in describing in some fashion, especially if we're in like a real world modeling context. When we're talking about a function, one thing that we often talk about are the x or the y intercepts. Those are the places where you're crossing like the y-axis. So that's like a y-intercept there at 0, 4. The other thing that we're also going to be interested in talking about are the x-intercepts. So these places where we're crossing the x instead of the y-axis. And what you'll notice there is that the x-coordinate is always something, but the y-coordinate is always 0. And that's because to be on the x-axis, you can't go up or down at all. You have to have that y value of the coordinate to be nothing. The other thing that we talked a little bit about is that sometimes for a function, you might have a maximum and you might have a minimum. You don't always have these. Sometimes you might have a bunch that are all the same. So you could say there's like some relative maxes and mins. But sometimes with a graph, you'll have an absolute high point and an absolute low point. And we usually express those as some kind of coordinate. So I might say from 3, -3 for the min there. For the max, I might say something like -4, 8. We usually specify where the max or the min is located. And that's usually with a coordinate discussion. The other thing we started to talk about is this idea of the domain versus the range of the function, as well as intervals for where the function is increasing or decreasing, or maybe even staying constant. Here's where we're going to start to kind of really focus on how to express that in mathematical terminology. We want to have some consistent way of saying that there's a whole set of values for which that behavior is happening. And we usually specify that for those intervals, it's when x starts at this value and it stops when x ends at some other value. So we go from beginning to end in terms of the inputs. So for example, if I wanted to write an interval for which my function is decreasing, I notice that the function starts decreasing when x is -4. It decreases all along the red part of the graph until x equals 3, and then it stops. It switches to increasing. So if I wanted to write that for a reader, I might say a few different things. I could say from x is -4 until x is 3, very verbally. But we also have some more symbolic ways to write that. And one way that we could say that is by using like a set of inequalities. So I can say x is greater than -4, but it's also less than 3. That's one way to do it. There's also something called interval notation. And we'll kind of explain that and work with a little bit more today as we go. If I wanted to write this in interval notation, the thing that kind of throws some students off on this is that it looks a lot like a coordinate in some contexts. Here, if I write in parentheses -4, 3, a lot of people are going to think that's like a location right there on the graph. That's not necessarily what we're saying if we're in the context of an interval. We're saying that that behavior begins when x is -4, it continues until x is 3, but it's not necessarily behaving that way on those one coordinate locations on the very end of the graph. So we get a little more specific there in that context. And again, we'll play with that a little more as we move through today's lesson. Here in the notes, I want to open up with, on page 13, this initial table of values. I want to give you kind of a problem context to mull over and think about. We're going to use a lot of different representations to kind of reinforce these key ideas that we saw in our first lesson. So here, we've got a scenario where three friends, Alonzo, Maria, and Sierra, they're all floating down a river in a bunch of inner tubes. Might be some river here in Colorado, so maybe it's the Platte, maybe it's the Green, maybe it's the Colorado. There's a lot of different places in the state where you can actually do this. I think this picture here is taken from Vail, Colorado, where a bunch of people are just kind of floating down the river there. And really, you're not really doing anything. You're just kind of letting the current of the water pull you as you move from point A to point B over time. They're all floating down the river together. So we'll assume that they're all maybe on the same big inner tube, or they're all kind of like linked up in smaller inner tubes, but they're moving as one big group. And what they're trying to figure out is maybe how the depth of the river is changing as they go from beginning to end on their trip. We'll also talk about on the next example the total distance that they've covered, just sort of floating along from beginning to end. What we notice here is that Maria is recognizing that they seem to be moving faster at different times than the other. Alonzo is noticing that the depth of the river is changing as they float along. Sometimes the river's kind of shallow, sometimes the river's kind of deep. He's collected some data about the depth of the river in 10-minute intervals from beginning to end. So their trip lasts a total of 2 hours. Alonzo's got some collected data here. What I want you to take a look at in the table are the things that you notice. What I want you to think about here are maybe where are some places in the trip where the depth seems really shallow or really deep. I also want you to think about, say, maybe where the depth is increasing or decreasing over time. And then from there, maybe think about like the domain and the range for the data set. How might you describe these things? So take a moment and kind of mull that over, pause the video, and we'll kind of pick back up in maybe about a minute or so. All right. So we've got a table of values. Alonzo's just been kind of marking it down every 10 minutes as they go. We'll assume he's got some sort of tool to check the depth of the water. Maybe they have like a long oar to help them paddle if they get kind of in a weird spot on the river or something. We'll notice that time goes from 0 to 120 minutes. We're going to refer to that as the domain of the relationship. The reason I'm saying time is the domain is that time doesn't really start or stop for anything, right? It just kind of goes. It's not being influenced by anything other than maybe gravity for those of you guys that are into like physics and science and stuff. Depth, on the other hand, though, that's very much changing depending on what time it is in the trip, right? It's dependent on the time. So anytime I've got like an independent variable like time, that's usually the domain. If I have a dependent variable like depth, that's going to be the range of the function. So I might say for the domain that this goes from, say, 0 all the way up to 120 minutes. I might represent time with the variable t. If I was writing this with inequalities, I'll say t is kind of sandwiched between 0 and 120 minutes. You'll notice here that I use less than or equal in my inequality to say that it can be 120 or 0 at the ends of the interval. If I'm talking about the range here, I might use a different variable like d to represent the depth measured in feet. What I want to think about here is like what's the lowest value for the depth and what's maybe the highest value before I write my interval. So I'm kind of scanning through the table here, and what I notice is that 90 minutes in the trip, there seems to be like a maximum depth of 12 feet. From there, I might also be interested in trying to pin down maybe if there's a minimum depth. So as I look through some of these values for the depth, I'm going to notice that there's two different places where the depth is only 4 feet deep. So it's fairly shallow in that river. It's right off the bat when they launch the trip. It also happens about halfway through their trip, about the 60-minute mark. Now, students will often ask, is there a way to say that there's a minimum here if they're really one and the same? We might have a conversation here where there might be like relative minimums in these two ranges. There might be like a relative minimum at about the 60-minute mark and another one at the 0-minute mark. If there's two of them that are exactly equal, we usually don't say that there's an absolute minimum. So it might be helpful to note that a low point in the depth is maybe 4 feet, but I might not necessarily say that there's a minimum given that there's two competing values. Over here on the left-hand side, though, I can definitely say that there's a y-intercept. When time is 0, the depth is 4 feet. So that's definitely fair game. So to kind of put that all together to have the conversation for the range, I might say that the depth is between 4 feet and 12 feet deep. And you'll notice in my inequality there that I use less than or equal. So I got D is greater than or equal to 4 and less than or equal to 12. That's only one way to write it. Another way to write it with something like interval notation, and I'll do this in kind of a different color, is to say, okay, I'm going from 0 until 120 minutes in the domain. I'm going from 4 until 12 feet in the range. I've got to specify, though, with my symbols, whether I can be that value or whether I can only get close to it but have to exclude it. So in interval notation, we usually write a squared off bracket around the values in that collection to say that you can be that number. So we use a bracket when it's like less than or greater than or equal to. We use a parenthesis when it's like strictly less than or strictly greater than, when you can't quite get that value. So I've got a max, I've got a y-intercept, I've pinned down the domain and the range. Another thing that I might think about is where things are increasing or decreasing. What I'm noticing early on in their trip is that from like the 10-minute mark until the 30-minute mark, the depth of the river seems to be going further and further down below them. It's increasing, right? But then from the 30-minute mark until about the 60-minute mark, it seems to be getting shallower. So the depth is decreasing in that particular part of their trip. Then as I go from like the 60-minute mark to the 90-minute mark, I'm noticing there that the depth seems to be increasing again, but then it changes in the last 30 minutes of their trip from the 90-minute mark to the 120-minute mark. It seems to be getting shallower again. So the depth is sort of like undulating in the graph. It's going up and going down and going up and going down. If I wanted to express that using like intervals or inequalities, I'm going to talk about the times in that. So for example, if I'm working on, say, the different time intervals, what I'm going to be noticing on this is that from, say, the first 30 minutes, I need to begin this at 0 minutes. I need to go until 30 minutes. What I'm usually going to do in that given context is I'm going to say with parentheses in interval notation that I'm increasing. And the reason I'm using parentheses there is if you look at the 30-minute mark, it's kind of a local or relative maximum. It switches from increasing and then it switches to decreasing. So right at the 30-minute mark, it's not really doing either. It's kind of hitting like a top part of a hill on the graph. So if I can't say it's either increasing or decreasing, we usually exclude that in interval notation. We'd use parentheses in that context. So there's a lot of information that we can glean from the table here. It's maybe a bit of a non-standard way to do this sort of analysis. We'll maybe go back to more familiar territory here on the bottom of page 13, where you've got this graph. Now, this graph was drawn by Maria. Maria is floating along the river with her friends. She's got a GPS unit that's actually tracking her location. She's set it up to track the distance down the river that they've floated from where they started until when they end 2 hours later. So what I want you to think about here is the same thing. Given a different representation, what are some of the key features that you notice on this graph? Would you say that there's like a maximum or a minimum? Does it seem to have y-intercepts or x-intercepts? Would you say that there's like intervals on which it's increasing or decreasing? All the big ideas there. I want you to kind of take a minute and mull it over for a second. All right. So in this particular context, we have Maria, who is floating along the river. She's tracking their total distance away from where they started. And she's tracking this, I think, in thousands of feet there. So they actually float quite a long way away from where they started. A long 2 hours there. It looks like they get up to maybe like 15 or 16,000 feet away from where they started. So they go almost like 3 miles downriver in this context. If I'm thinking about, say, intercepts, I'm going to notice that I have like a y-intercept here approximately at 0, 0. That makes sense, right? Because if they start the trip, the very moment they begin floating down the river, they haven't really gone anywhere. Over here at the end, though, I'm going to notice a maximum. Here, I'm going to see that I have a maximum when time is 120 minutes. This corresponds approximately to like 15,000 feet down the river. So a little under 3 miles away in that context. I don't really see, in this case, like a minimum in the middle of the graph. If you think about the left-hand side there with the y-intercept, you might be able to make the argument that that's also the min, because it's the absolute lowest point of the graph. It just so happens to be also be a y-intercept at the end point there. So sometimes that happens. That might be fair game to say that that's a minimum. If I'm thinking about the domain here, I'm still working in time, and that's still measured in minutes. So I might be able to say that the domain here is really no different than what I saw for my other problem. But the range in this case, this is kind of different, right? Now I'm measuring in thousands of feet away from the beginning. So if I wanted to write this in interval notation, I might use brackets to say I go from 0 to 15,000 feet away from the beginning point. I could write that with inequalities, where I say 0 is like less than or equal to d, which I'll use to represent distance in this context, which is less than or equal to 15,000. Usually we'll use interval notation. I'm just kind of showing this a multitude of different ways to see that how we can express it. The other thing that I notice about this graph is that it's never really decreasing. If I kind of like highlight and sketch in green the shape of this graph and how it's changing as they float down the river never like stops and flows backwards, right? It's only ever flowing in one direction. So at any moment in time, they're always going to be increasing the distance from where they began as they get closer and closer to the end point. So sometimes you might have a function where there's only one kind of behavior. Some functions like this guy are always increasing and never decreasing. You might also see functions that are always decreasing and never increasing. So as we work through some of these different key ideas, right, the key characteristics, you'll tend to see that happen on occasion. So to kind of bring it back together here and get a little more practice with identifying the key characteristics, I want you guys to sort of push ahead into part 3. Take maybe like 5 to 10 minutes, sort of work through some of these like true or false, agree, disagree statements. I think in total, there's something like 8 of them roughly. I want you to work through these one by one with your partner at your table. I want you to see whether you agree with it or you disagree with it, but also come up with maybe a justification as to why. Some of these, there might not necessarily be one right answer, but we'll kind of bring it back together and discuss real fast, and we'll get ready to close it out for the notes today. All right. So on the first one here, we have a statement that reads that the depth of the water increases and decreases through the 2 hours that they're floating down the river. We saw previously in our graph that the distance away from the starting point is always increasing, right? The river never stops and goes backwards and brings them back closer to where they began. It's only going one way. So if I was looking at this graph and thinking about distance, I think it would be always increasing, right? So that would be a false statement. But we're not really focusing on distance, are we, in that question? We're taking a look kind of back at the table. And we're saying, okay, what about the depth of the river? Well, the depth is kind of changing from increasing to decreasing. It's sort of undulating and changing and sort of cycling through those depths the further along you go. So I would say for that first question there that I definitely agree. If we look at, say, the second question, the distance traveled is always increasing. I agree with that statement. Based off of what we saw from the graph, the river's not stopping and flowing backwards. It's only going one way. So it's kind of impossible to stop moving unless they had like something to anchor themselves with in the river. So they're staying put in some fashion. If I go to the next one, C, the distance traveled is a function of time. Where I've got to be careful is that to call something a function is a very specific meaning. For any one choice in time, if you look at this graph, so if I choose, say, like the 50-minute mark or the 100-minute mark, I'm going to have kind of maybe a hard time pinning down exactly how far away from the origin they are. But the better question here is whether there's only one answer. At the 50-minute mark, they're one distance away. At the 100-minute mark, they're a little further away, but they're not in two places at the same time, right? That's impossible. That can't happen. So for this particular model, we would definitely say that that's a function relationship. There are some instances where you might have a relationship where for one input, it makes sense to have multiple possible outputs. That would technically fail to be a function. So for this third question, I find myself agreeing with that given statement. So I would say here, distance traveled, definitely a function of time. This question here, the fourth one, the distance traveled is greatest during the last 10 minutes of the trip than during any other 10-minute interval of time. It might be helpful to kind of go back and look at the graph here. What they're saying is that in the last 10 minutes of the trip, so if I highlight like from here to here on the graph in green, it looks like they're traveling maybe 3,000 feet or so. What we're trying to make an argument for is whether that's the fastest increase that we see in the entire graph across a 10-minute span of time, right? Now, one thing that I'm noticing is if you go back a little bit further to the left, from like the 30-minute mark until the 40-minute mark, there's a span of time there where they're increasing by kind of about the same distance. That's a pretty steep part of the graph, but it looks like it's about equal to that last 10-minute mark. If I look elsewhere, so say, for example, over here, from like the 60-minute mark to the 70-minute mark, I'm going to notice there the steepness is kind of tapering off, right? They're not clearing as much distance in 10 minutes as they were in the red or the green interval. So I might say there maybe that I agree. It's kind of hard to exactly measure that red interval's change in distance over time, the slope of that kind of area there. But you could also maybe disagree and say that that last 10 minutes is roughly equal to the 10 minutes from 30 to 40. So they're kind of really the same and it's not the greatest one on the end. I wouldn't say that there's one obvious answer to that particular question. As we go from there into our fifth question, the domain of the distance time graph is all real numbers. Well, when you think about the distance that you're traveling versus time, to say that it's all real numbers is to say that you can get values kind of in between the grid lines, right? And when you have a smooth, continuous graph like they drew there for distance, that's definitely what they're trying to argue there. If it was a set of just kind of like discrete, disconnected dots on the graph, that would be more like the natural numbers for the domain. So I find myself agreeing on this question. For the sixth one, the y-intercept of the depth of water over time function is 0, 0. So if I think about depth versus time, that goes back to like our very first table. What I'll notice there at the very beginning is that the moment they start the trip, they're not at a depth of 0 feet. They couldn't be floating there, right? They'd be kind of stuck on land. So I disagree with that particular question. I'd say that the y-intercept there is more like 0, 4 instead of 0, 0. If I take a look at this question, the depth of the water is never 11 feet. It's also a bit of a toss-up there, I'd say. I wouldn't necessarily say that there's only one answer to that question. As I go and I take a look at, say, the table, I would definitely say here that I've got some discrete data. But you could maybe make the argument that the depth of the river is going to kind of gradually change. It's not going to like suddenly jump and suddenly drop. It's always going to have kind of like a smooth gradient to it, right? At least in the real world. So maybe if there's like a maximum depth of 12 somewhere in the trip, there's maybe a depth of 11 feet. But I could also see an argument the other way to say with that discrete data, we're not seeing an output of 11. There's not necessarily just one right answer in that context. Here, the range of the distance time graph is from 0 to 15,000 in brackets. That's interval notation for the range in that case. I definitely agree with this given statement. The domain of the depth of water with respect to time is from 0 to 120. I also agree in this context. Their total float trip takes about 2 hours time. There's a beginning moment, there's an end moment, and they can actually be at those moments of time and still get a measure for the depth of water. So I think this is a fair statement. The range of the depth of water over time is from 4 feet to 5 feet inclusive. I disagree with that statement. If you take a look at the table of values, we saw there that the range goes anywhere from 4 feet up to 12 feet. To say that it goes from 4 to 5 is to say that you can't go any deeper than 5 feet, which we know for sure is false because there's a point in their trip where they're at a 12-foot depth. So we can definitely shut that question down. That one's definitely going to be a false statement. As we go from there, the distance time graph has no maximum value. You can maybe make an argument that there's no maximum in the middle of the trip, but at that very end point, we saw that maybe there was. Right at the very end, they've gone about 15,000 feet. It's at the very end of the trip, so it's an end point of the graph, but I would say that there is a maximum, so I disagree with that one. The depth of the water reaches a maximum at 30 minutes. So if I go back to this particular question with the table, and I'm looking at the depth at 30 minutes, it's 10 feet deep, and relative to the area around it, that seems to kind of be a deep part of the river. That's not necessarily, though, to say that that's the deepest point that the river goes, at least in their 2-hour trip. So sometimes you might have a relative minimum or maximum where compared to things around it, it's really high or really low, but it's not necessarily an absolute maximum in that case. So I would disagree with that statement. The maximum value appears to be 12 in that case. So as you're working through some of these, kind of analyzing the relationship with that table and that graph, ultimately that's what's going to allow us to sort of figure out the solutions for these. I think you guys can probably work through the rest of those based off of where we started the process. So I kind of want to jump to this last question, the ready for more question, mainly because this one gets a little tricky. This one's kind of a weird one that they ask us to construct. What they want us to do here is take the data given in the table and the graph as we started our notes to create a third graph where we're going to track distance versus depth. And what's kind of weird here is we're going to need to figure out like what's a depth at one moment of time and correspond it to a distance at that same moment in time. There's no time that's being used in this case. So they're saying that the distance is going to run on the x-axis, the independent variable, and they want the depth to run on the y-axis to be the dependent variable. So what I did is I took most of the data points from that first table. I didn't do all of them. I figured out where at that given time the corresponding distance was on Maria's graph. So for example, at the beginning, we're 4 feet deep, but we haven't gone anywhere. I got a new coordinate in my table here, 0, 4. Similarly, if I take a look at when the depth is 8 feet, I think that's like 20 minutes into the trip. 20 minutes into the trip on Maria's graph, they're about 6,000 feet away from where they started. So you kind of have to merge these two things together. The outputs of the graph and the outputs of the table are creating a new table in this context. Once we have some of those values, we can sort of plot them out on the graph here to the right and get this kind of relationship. Now, what I want to point out here is whether we believe that this is continuous or discrete. Given the way that I've constructed the graph here, if I've got like these points that are not connected with like a smooth continuous curve, we would say that this is a discrete function. So the domain in this case of the depth, we'll say here that that's ultimately going to be something like an independent variable that's represented with natural numbers. Now, what's kind of interesting here is if you take a look at the way that I constructed my graph, where I do depth versus distance, there's a depth for which there's two different distances, right? If I look at a depth of 12 feet, I'm going to notice there that that happens a couple of different times, right? There, I'm going to see something like a depth of 12 has a distance of 7,000 feet, but also 12,000 feet. If I've got that repetition there, that means that this relationship as I graphed it is not necessarily a function relationship. So it's kind of tricky to do the construction on this. You got to take the two existing things and kind of pull those two outputs together in a table. And then once you have that, you can sort of construct it and work from there to make some statements. So to sort of close things out for today, what I want to overview is just kind of the big ideas from the lesson. One of the things that we talked about is how to identify key features when you don't have a graph. Sometimes you might have a different format like this guy, a table of values. You can still think about things like the domain and the range, intervals of increasing versus decreasing, X and Y intercepts, maxes and mins. It just might be a little more difficult to spot them, right? We have to kind of think about what these variables are describing as things change for the input variable. So I found here a y-intercept. I found a maximum. I didn't necessarily find a minimum. I might be able to argue that it's the same thing as the y-intercept, but I also identified some intervals of increasing versus decreasing behavior. You'll notice here for increasing and decreasing, I wrote it in interval notation. That's kind of the other thing that I want to really focus on as the big takeaway from today's work. When we're talking about sets or spans or collections of values from beginning to end, there's a very specific way that we do that in math. If you write it as interval notation, it can sometimes be confusing for students because on occasion, it looks a lot like a coordinate. In a context where you're given an interval, it's always talking about from beginning to end. So if I wanted to express, say, a certain behavior from 0 to 30 seconds, so when, for example, the depth is increasing in the river, I can do that a couple of ways. I can use interval notation where I go from 0 to 30, or I can use inequalities where I say if t is time, then t is stuck between 0 and 30 seconds. You'll notice here that I used a less than or equal to say that the function starts increasing right off the bat. If something can be used as a less than or equal to, it's going to have a bracket in interval notation. We say that it's inclusive of that value. On the other hand, though, at the 30-second mark, I noticed for my function that it switches from increasing to decreasing, so it's kind of neither. If I have a strict inequality, if I'm excluding that value in the interval, that's where we use a parentheses. So in an interval where you see like double parentheses, I think a lot of students are quick to assume that that's a location, but it's actually a set, a collection, a span of values between 60 and 90, for example. So you got to be really careful there. Another thing to point out is that if you have like two intervals for which a behavior is happening, so if I'm thinking about depth where it's changing and increasing, it happens from 0 to 30 seconds, and then again from like 60 to 90 seconds, or I think it's minutes for our depth table. I think I had to change the wording there. I want to represent both of those, right? So I can use an and statement in English or with inequalities. I can say 0 is less than or equal to t, which is less than 30, and 60 is less than t, which is less than 90. When we're using set notation, if I use the keyword and, there's a symbol that we use for that. That's like this big U. We call that a cup or a union. It's a special math symbol that means this and this, or this or this in this given context. So when you see that particular symbol, it's saying that both of these intervals are true. It's just kind of a more condensed way to use a symbol to express the language of it. We're mainly going to focus on interval notation as we go forward in the unit. What I really want to point out on this slide is that it's not the only way to express it or to think about it. So if you're feeling a little uncomfortable with interval notation, don't fret. We're going to practice with it. Maybe focus on inequalities or English descriptions first, and then try and use that to switch into interval notation. Otherwise, though, I think that's going to close us out for our time today. As we get going, I want you guys to start working on the Ready, Set, Go practice for 3.2. If you have any particular questions from some of the notes today, definitely hold on to them. Definitely keep them in mind so that when I'm back on Monday of next week, for our B day. We can sort of work through it as a warm-up maybe and take a look from there. Otherwise, though, I hope you guys have a great weekend. I'll see you guys next time.